Have you ever stopped to think about what actually happens to a solar panel's brain when a bird poops on it? I know, it sounds like a joke, right? But honestly, it is one of the most frustrating, real-world problems in renewable energy today. You see, solar panels rely on these highly sophisticated control systems to harvest the sun. But a simple shadow, whether that's from a passing cloud, a neighbor's chimney, or yes, a well-aimed bird dropping, can completely scramble that system and cause massive power losses. So welcome to The Explainer. Today we're diving into the fascinating intersection of electrical engineering and computer science. We are going to look exactly at how artificial intelligence, specifically deep reinforcement learning, is swooping in to rescue solar energy extraction from the utter unpredictability of the natural world.
Okay, let's dive into this. Here is our roadmap for today. 1. The solar shading problem. 2. The power curve trap. 3. AI to the rescue. 4. Training the solar agent. 5. Optimization inspired by lightning. And finally, 6. The future of smart solar.
All right, starting off with Section 1, the solar shading problem.
Every single modern solar PV system out there has this sort of brain, and it's called MPPT, which stands for Maximum Power Point Tracking. This is absolutely crucial. It's the essential control system that allows for the absolute best energy extraction. Because the sun isn't static. Temperatures change, cloud cover shifts, irradiance fluctuates. The MPPT is constantly adjusting the electrical operating point of the panels, specifically tweaking the voltage, just to make sure the system is pulling the maximum wattage possible at any given second. And when the sun is shining perfectly and uniformly, traditional MPPT works great. It does exactly what it's supposed to do.
But here is where things go a little sideways. We call it the partial shading condition, or PSC. When shadows from buildings or utility poles or our aforementioned bird droppings cover just a tiny fraction of the solar array, it causes uneven illumination. Now, to prevent those shaded, darker solar cells from overheating and literally destroying themselves, the system uses what are called bypass diodes to quickly route electricity around the shaded spots. Sounds like a good fix, right? Well, it creates a massive side effect. It severely distorts the system's power curve, creating all these multiple fake peaks or local maxima that totally confuse the traditional MPPT brain.
Which brings us to Section 2, the power curve trap. Picture this for a second. Think of the power voltage curve like a mountain range covered in thick, heavy fog. The ultimate goal of our system is to climb to the absolute highest peak, the global maximum power point, because that is where the most energy is harvested. Under perfectly clear, uniform sunlight, there's just one peak. Boom, it's an easy climb. But under partial shading, those bypass diodes we just talked about, they basically create a jagged, messy mountain range with several smaller peaks scattered around. Now, traditional algorithms, like the incredibly common Perturb and Observe method, act exactly like a blindfolded climber. They just kind of feel the ground with their feet, stepping upward until they finally hit a peak. Once they feel the ground slopping down in all directions, they stop, thinking they've made it. But because of the fog, they have absolutely no idea they're only standing on a small foothill, a local maximum, while the true summit, the global maximum, is literally on the next ridge over. It results in terrible energy losses. So what we really need is a climber with a drone. A system that can actively scan the entire environment and learn how to find the true summit. And that is exactly what deep reinforcement learning brings to the table.
Moving on to Section 3, AI to the rescue.
The landscape of deep reinforcement learning algorithms is incredibly vast and powerful. You see, traditional methods require these rigid, strictly predefined mathematical models of the environment to work. But DRL, specifically the model-free branches, doesn't need to know the physics of the solar panel in advance. It's a real game changer. It solves highly complex control problems with massive state spaces just by naturally interacting with them, trial and error style.
Actually, there's this quote from the source material that I absolutely love. It says, "Unlike static operating points, dynamic response learning allows the controller to develop an optimal control strategy through never-ending dialogue with nature." I mean, it's almost poetic, right? The AI agent isn't just mindlessly running a static equation. It's constantly talking to the environment, monitoring the shifting shadows, the changing light, and dynamically adapting its strategy to aggressively hunt for that maximum power. Let's look at how this works in Section 4, training the solar agent.
To actually pull this off, the researchers framed the problem using something called SEDRL-MPPT, or Scanning-Enabled Deep Reinforcement Learning. It really boils down to three fundamental things. First, the state. This is what the AI literally sees, real-time electrical parameters like voltage and current. Second, the action. This is what the AI actually does. tweaking the duty cycle of the converter. And third, the reward. This is the whole shebang. If the AI's action extracts more power, it gets a positive reward. Good job. If power drops, it gets a negative reward. Through thousands and thousands of iterations, it learns the exact sequence of steps to effortlessly bypass those fake mountain peaks. Plus, the scanning-enabled part means it periodically sweeps the voltage range just to double-check, making sure it hasn't missed a better peak as the shadows move across the panels.
Section 5. Optimization inspired by lightning.
So, once the AI finds that maximum power, we still need incredibly stable voltage and current controllers to actually send that power to the grid without dangerous spikes or weird oscillations. To perfectly tune these controllers, researchers use another meta-heuristic algorithm, and this one is totally inspired by nature, the Lightning Attachment Procedure Optimization, or LAPO. Think about how a lightning strike actually works in the real world. Clouds build up immense energy. A downward leader reaches out, kind of exploring different paths in the air. An upward leader rises from the earth to meet it, and when they finally connect, boom, the optimal path is instantly found, and the flash is composed.
Now, underneath that incredible lightning analogy is some seriously intense computational logic, specifically the Improved Lightning Attachment Procedure Optimization, or ILAPO. Just like how natural lightning branches out to explore the sky before finding that single most efficient path down to the ground, this algorithm perfectly balances exploration, which is searching through the data, with exploitation, which is locking onto the absolute best controller settings. It iteratively adjusts the controller gains to minimize errors, and it acts incredibly fast.
Which brings us to our final part, Section 6, the future of smart solar.
And the best part? Engineers aren't just leaving this in theoretical code. They are rigorously testing this whole setup in highly detailed grid environments. For instance, in a MATLAB simulation mapping out a standard residential rooftop installation, they use a two-stage power conversion architecture. First, the solar array feeds into a boost converter, where our AI agent is constantly tweaking the duty cycle to squeeze out every drop of power. Then, that power moves over to an inverter, which is tightly regulated by our lightning-optimized controllers, ensuring the electricity is perfectly primed and stable for your home or the grid.
To put this into perspective and show you the real-world stakes here, the simulations test this system handling an array producing about 2,400 watts of electricity. And thanks to these cooperative control strategies between the AI and the optimization algorithm, it effortlessly maintains a highly stable 400-volt DC link voltage. It responds dynamically to sudden massive shifts in sunlight, virtually eliminating the lag and instability that typically plague older residential solar setups. It's wildly efficient.
So, what does this all mean for us? The crucial point to take away from all this is that combining SCDRL MPPT with those lightning-optimized controllers pretty much solves the partial shading problem once and for all. It maximizes energy extraction, it vastly improves system stability and power quality, and honestly, the most amazing part is that it does all this without needing a predefined mathematical model of the solar array. The system simply learns, adapts, and performs on the fly, in real time.
It really makes you step back and think, doesn't it? We are actively looking at a near future where our energy grids aren't just dumb, passive wires, but they're living, learning systems engaged in a continuous, high-speed dialogue with the environment. Which leaves us with a really fascinating question. If AI can learn to perfectly harvest the sun, dodging clouds and shadows in real time, what other forces of nature will it master next? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.